Right now, at this very moment, a spacecraft the size of a small car is flying through territory no human has ever explored. It has been flying for over 47 years. It left Earth in 1977. And just recently, the data it sent back has left scientists genuinely confused. Not the kind of confused where they say, interesting, and let's study this more. The kind of confused where they said, and I quote, "We did not expect this." If you want to understand what Voyager 2 actually found out there, and why it matters more than most space news you will ever hear, stay right here. Because this is not a story about a spacecraft. This is a story about the edge of everything we know, and what's waiting on the other side. And if you're new here, subscribe right now and hit the bell. We cover real space science explained simply every week. You don't want to miss what's coming. Let's start at the beginning, because the story of Voyager 2 is one of the most incredible things humanity has ever done. It was August 20th, 1977. NASA launched a spacecraft from Cape Canaveral in Florida. They called it Voyager 2. 16 days later, they launched Voyager 1. Both were headed out into the solar system on a grand tour of the outer planets. Now here's what most people don't know. The reason NASA launched when they did, August and September of 1977, was because of a rare planetary alignment. The outer planets, Jupiter, Saturn, Uranus, and Neptune, were lined up in a way that wouldn't happen again for another 176 years. This alignment allowed a spacecraft to use the gravity of each planet to slingshot itself to the next one, saving enormous amounts of fuel. NASA called this the Grand Tour, and they had one shot at it. Voyager 2 was built to last maybe 5 years, just long enough to fly past Jupiter and Saturn. That was the plan. But the spacecraft kept going, and going, and going. In 1979, Voyager 2 flew past Jupiter. It sent back stunning images of the Great Red Spot, a storm bigger than Earth that has been raging for hundreds of years. It discovered active volcanoes on Jupiter's moon, Io. Scientists were amazed. No one had seen volcanic activity anywhere outside of Earth before. In 1981, it reached Saturn. It flew through the rings, measuring their thickness, their composition. Scientists discovered the rings are made mostly of ice particles, some as small as grains of sand, some as large as houses. Voyager 2 sent back images that changed our understanding of Saturn forever. Then something interesting happened. Instead of shutting down or running out of fuel, Voyager 2 kept going. NASA made a decision. They would send it to Uranus and Neptune too. No spacecraft had ever visited those planets. No one had ever seen them up close. In 1986, Voyager 2 reached Uranus. It discovered that Uranus has a magnetic field tilted at an incredible 59 degrees from its rotation axis. It found 10 new moons. It measured winds blowing at 250 meters per second. Uranus turned out to be far stranger than anyone imagined. In 1989, it reached Neptune. This was the grand finale, the last stop in the solar system. Voyager 2 discovered that Neptune has the fastest winds in the solar system, blowing at over 2,000 kilometers per hour. It found a massive storm called the Great Dark Spot, similar in size to Earth. It discovered that Neptune's largest moon, Triton, orbits backwards, opposite to the direction Neptune spins. Triton has geysers that shoot nitrogen gas several kilometers into the sky. After Neptune, there were no more planets to visit. Voyager 2 was heading into the unknown, into the vast dark space between the solar system and the rest of the universe, and that is where things got really interesting. To understand what Voyager 2 found, you need to understand what it was flying through. Our sun doesn't just sit there and shine light. It constantly releases a stream of charged particles, electrons, protons, and other particles, flowing outward in all directions. This stream of particles is called the solar wind, and it doesn't stop at the last planet. It keeps going far beyond Pluto, far beyond anything with a name, pushing outward into space. As this solar wind flows out, it creates a bubble around our solar system. Scientists call this bubble the heliosphere. Everything inside this bubble, all the planets, all the asteroids, all the comets, is inside this protective shell created by our sun. Now, the solar wind doesn't flow outward forever. Eventually, it slows down. It runs into the thin gas and particles that fill interstellar space, and the space between star systems. There's a boundary where the solar wind slows and becomes chaotic. Scientists call this the termination shock. Beyond the termination shock, there's a region where the solar wind is still there, but it's hot, turbulent, and compressed. This region is called the heliosheath. Think of it like a buffer zone. And then there's the final boundary, the place where the sun's influence completely ends and true interstellar space begins. This boundary is called the heliopause. For decades, scientists had theories about what the heliopause would look like. They had mathematical models, they had simulations, but no spacecraft had ever crossed it before. Voyager 1 crossed the heliopause in August 2012. That was historic. But here's the thing. Voyager 1 was on a different trajectory than Voyager 2. It crossed the heliopause in a different location, at a different angle in a different part of the solar system's outer boundary. Voyager 2 crossed the heliopause on November 5th, 2018. And what it found there, and in the years since, has rewritten what scientists thought they knew. Let me tell you about the first strange thing Voyager 2 found. When Voyager 2 approached the heliopause, its instruments detected a sharp jump in the density of cosmic rays, high-energy particles that come from outside the solar system. This was expected. The heliopause acts like a barrier, and scientists knew cosmic ray density would increase as Voyager 2 crossed it. But the readings were different from what Voyager 1 had measured at its crossing point. The cosmic ray intensity jumped at a different rate. The particle environment was not the same. This told scientists something important. The heliopause is not uniform. It's not a smooth, consistent boundary all the way around the solar system. Different regions of the heliopause have different properties. The shape and structure of this boundary is more complex than the models predicted. Think about what that means. The protective bubble around our solar system, the thing that shields us from much of the radiation and particles coming from the rest of the galaxy, it's not a neat sphere. It's lumpy. It's irregular. Different parts of it behave differently. That alone would have been a major discovery. But Voyager 2 wasn't done. Here is the second thing Voyager 2 found. And this one is strange. As Voyager 2 crossed the heliopause, it measured the temperature of the plasma, the charged gas, in that region. And the numbers it sent back were startling. Right at the boundary, Voyager 2 detected plasma temperatures of around 50,000 degrees Celsius. Not inside the solar system, right at the edge, at the wall between our solar system and interstellar space, 50,000 degrees. That is nearly 10 times hotter than the surface of our own sun. Now this might sound impossible. The heliopause is far away from the sun, far away from any heat source. How can the temperature there be that extreme? Scientists were genuinely puzzled, and they still don't have a complete answer. The current best explanation is that this superheated plasma forms when the solar wind, moving outward, crashes into the interstellar medium moving inward. The collision creates an enormous amount of heat, concentrated right at the boundary. But here's what makes it even stranger. The data from Voyager 1's crossing didn't show this temperature spike quite as dramatically. Again, the two probes, crossing the same type of boundary in different locations, finding different things. The heliosphere is not what we thought it was. The boundary of our solar system is not a simple wall. It's a complex, dynamic, strange region that we are only beginning to understand. Now let's talk about the third discovery. And this is the one that really made scientists scratch their heads. When Voyager 2 crossed into interstellar space, it began measuring the density of the plasma around it. As it moved farther from the sun, deeper into true interstellar space, scientists expected to get a reading, a baseline density for the space between stars. What they found instead was that the plasma density kept changing. And not in a random, chaotic way. It was increasing in a way that didn't match the models. Scientists published a paper about this in 2019 based on Voyager 2's data. They found that the density of the plasma in the region just outside the heliopause was higher than they had predicted. And it was higher on the Voyager 2 side than on the Voyager 1 side. This matters because it tells us that the interstellar medium, the gas between the stars, is not uniform either. Space between stars is not empty nothingness that's the same everywhere. It has structure. It has regions of higher and lower density. And those regions interact with the heliosphere in ways that change its shape and size. In 2020, scientists used Voyager 2's data to recalculate the thickness of the heliosheath, that buffer zone between the termination shock and the heliopause. On Voyager 2's side, it was thinner than on Voyager 1's side. This suggests the heliosphere is not a sphere at all. It's pushed and pulled into different shapes by the interstellar medium pressing on it from outside. Some scientists now believe the heliosphere looks less like a bubble and more like a comet, with a rounded head pointing in the direction the sun is moving through the galaxy, and a long tail stretching out behind it. Voyager 2's data has helped refine this picture significantly. But wait, there's more. And this part is directly relevant to life on Earth, even if it doesn't seem like it. The heliosphere, the bubble of solar wind that surrounds our solar system, acts as a shield. It deflects much of the cosmic radiation coming from deep space. Without it, the amount of radiation hitting the inner solar system would be much higher. Cosmic rays are dangerous. They can damage DNA. They're one of the major concerns for long-duration space travel. Astronauts going to Mars would be exposed to much higher levels of cosmic radiation than astronauts in low Earth orbit. And if the heliosphere were weaker or smaller, Earth's surface would receive more of this radiation. Now, here's what Voyager 2's data adds to this picture. By measuring the cosmic ray environment on both sides of the heliopause, inside and outside, Voyager 2 gave scientists their first direct comparison from a second location. And the data shows that the heliopause is genuinely effective at blocking cosmic rays. The difference in cosmic ray intensity inside versus outside is dramatic, but the data also shows that the heliopause is not a perfect barrier. Some cosmic rays leak through, and the amount that leaks through varies depending on where on the boundary you are. This leakage could affect long-term climate patterns on Earth, biological mutation rates over geological time, and even the evolution of life. These are not science fiction ideas. These are areas of active research, directly informed by the data Voyager 2 is sending back. Let me step back and give you a sense of scale, because it's easy to lose track of how extraordinary this mission is. Voyager 2 is currently more than 20 billion kilometers from Earth. That's not a typo. 20 billion kilometers. The distance is so large that even traveling at the speed of light, 300,000 kilometers per second, a signal from Voyager 2 takes more than 18 hours to reach Earth. When scientists at NASA's Jet Propulsion Laboratory send a command to Voyager 2, they have to wait 18 hours for it to arrive. Then they wait another 18 hours for the response to come back. That's a 36-hour round trip for a single command and response. And yet they are still communicating with it. They are still receiving science data from a spacecraft launched in 1977 running on a power source that produces less electricity than a standard light bulb. Voyager 2 runs on a radioisotope thermoelectric generator, an RTG. This device uses the heat from the radioactive decay of plutonium-238 to generate electricity. When Voyager 2 launched, its RTG produced about 470 watts of power. Today, 47 years later, it produces around 250 watts. The power output decreases slowly as the plutonium decays. To keep the spacecraft running as power decreases, NASA engineers have been systematically shutting down systems that are no longer essential. Heaters have been turned off, redundant systems have been deactivated. The science instruments that survive are the ones that are most important for the mission. Currently, Voyager 2 is running 5 science instruments: a plasma science instrument, a low-energy charged particle detector, a cosmic ray detector, a magnetometer, and a plasma wave instrument. These 5 instruments are sending back data that is actively changing our understanding of the universe. Scientists estimate Voyager 2 will be able to operate at least one instrument until around 2025 to 2030. After that, as the power continues to drop, it will go dark. It will keep flying forever. There's nothing to stop it, but it will no longer be able to communicate. Now, let's talk about what Voyager 2 found specifically about the magnetic field, because this is one of the strangest discoveries of all. Inside the heliosphere, the magnetic field is dominated by the sun. The sun's magnetic field is carried outward by the solar wind, forming what scientists call the interplanetary magnetic field. This field rotates with the sun, creating a spiral pattern that extends throughout the heliosphere. Outside the heliopause, in true interstellar space, there's a different magnetic field, the galactic magnetic field, created by the combined effect of stars, gas, and other matter throughout the Milky Way. When Voyager 1 crossed the heliopause, it measured the direction of the interstellar magnetic field. This was the first direct measurement of the galactic magnetic field outside our solar system. The direction was surprising. It didn't match what scientists had expected based on observations of nearby stars. When Voyager 2 crossed the heliopause in a different location, it measured the interstellar magnetic field again. And here's what's interesting. The direction of the magnetic field measured by Voyager 2 was almost exactly the same as what Voyager 1 had measured. This consistency was unexpected. Scientists thought the galactic magnetic field might vary significantly from place to place. But the fact that 2 probes, crossing the heliopause in different locations, measured nearly the same magnetic field direction suggests that the galactic magnetic field in our local region of space is relatively uniform and well organized. This has significant implications for how the heliosphere interacts with the interstellar medium. The orientation of the external magnetic field affects how the solar wind and the interstellar medium push against each other. It affects the shape of the heliosphere. And it affects how well the heliosphere shields us from cosmic rays. By having 2 data points from Voyager 1 and Voyager 2, scientists can now begin to build a more accurate model of how our solar system sits within the larger magnetic structure of the galaxy. There's something else worth mentioning because it speaks to just how different the universe is from what we imagine. When most people think of space, they think of emptiness, vacuum, nothing. But that's not quite right. The interstellar medium, the space between stars, is filled with thin gas and dust. It's not a lot. The average density of the interstellar medium is roughly 1 atom per cubic centimeter. Compare that to Earth's atmosphere at sea level, which has about 7 times 10 to the power of 19 molecules per cubic centimeter. The difference is incomprehensible. But it's not nothing, and it's not uniform. There are regions called the local bubble, a cavity in the interstellar medium carved out by ancient supernova explosions, which our solar system is currently moving through. The edges of this bubble have different densities, different temperatures, different magnetic field strengths, Voyager 2's data is helping scientists map the properties of this medium right outside our solar system. It's the most direct measurement possible, not made with a telescope from far away, but by a probe actually there, actually sampling the environment directly. No telescope can give you that, only Voyager can. Let me tell you something that doesn't get talked about enough. In 2020, NASA temporarily lost contact with Voyager 2. Not because of a technical failure, because of maintenance work on the Deep Space Network, the global array of huge radio antennas that NASA uses to communicate with distant spacecraft. The antenna in Canberra, Australia, the only antenna capable of communicating with Voyager 2 due to its position in the southern sky, was being upgraded. For about 7 months, NASA could not send commands to Voyager 2. They could hear its signal, the carrier wave that tells them the spacecraft is still alive, but they couldn't send commands. Then, in November 2020, the antenna came back online. Contact was restored. Voyager 2 was still on track, still healthy, still sending data. There's something almost moving about this. A spacecraft so far away that it took 18 hours for a signal to reach it, going dark for 7 months, and then hearing its signal come back strong. Engineers who had worked on the mission for decades described the moment as genuinely emotional. Voyager 2 is the only human-made object to have visited Uranus and Neptune. It's one of only 2 human-made objects to have entered interstellar space. And it continues, day after day, to expand the frontier of what we know. Let's talk about what this means for the future. There are currently no missions planned to go where Voyager 2 has gone. No spacecraft is scheduled to cross the heliopause again. The next generation of space probes is focused on closer targets: the Moon, Mars, the moons of Jupiter and Saturn. This means that for the foreseeable future, Voyager 2 is our only source of direct data about the conditions at and beyond the edge of our solar system. Every reading it takes is irreplaceable. Every data point it sends back is a measurement no other instrument on Earth or in space can duplicate. When Voyager 2 finally goes dark, when the last instrument shuts down and the signal fades, we will lose a capability that took 47 years to build. Some scientists have proposed an interstellar probe mission, a dedicated spacecraft designed to travel beyond the heliopause and study the interstellar medium in detail. Unlike Voyager 2, which was primarily built to study the outer planets and whose interstellar mission was a bonus, an interstellar probe would be specifically designed for this environment from the start. It would carry more advanced instruments. It would be designed to survive the journey. And it would travel faster than Voyager, potentially reaching the heliopause in 15 to 20 years instead of 35. NASA has studied this concept seriously. The 2023-2032 Planetary Science Decadal Survey, the document that sets science priorities for NASA, included an interstellar probe as a concept worth developing. It hasn't been formally approved yet, but the scientific community is pushing for it, because the questions that Voyager 2 has raised are not small questions. They're fundamental ones. Why is the heliopause shaped the way it is? What is the detailed structure of the interstellar medium just outside our solar system? How does the heliosphere interact with the local galactic environment over time? Does the shape of the heliosphere change? Could it ever collapse? And what would that mean for life on Earth? These are questions that matter. And Voyager 2 has shown us that the answers are stranger, more complex, and more surprising than anyone imagined. Here's the final thing I want to leave you with. When Voyager 2 was launched in 1977, the people who built it, the engineers, the scientists, the technicians, many of them are gone now. The mission has been passed down through generations. Young engineers who weren't born when Voyager 2 launched are now the ones monitoring its systems, analyzing its data, writing the software updates that keep it functioning. The mission is older than the internet, older than most of the technology we take for granted today, and yet it continues. There's a phrase that gets used a lot in space science: building cathedrals. The idea is that some projects are so large, so long-term, that no single person or even single generation sees them through from start to finish. The people who lay the foundation never see the spires. The people who complete the spires never knew the people who quarried the stone. Voyager 2 is one of humanity's cathedrals, and what it has found at the edge of our solar system, the superheated plasma wall, the unexpected density increases in interstellar space, the non-uniform heliopause, the consistent galactic magnetic field, these are chapters in a story that will take generations to fully understand. We are not at the end of this story. We are barely past the beginning. The universe is far stranger than we imagined, far more complex, far more detailed. And Voyager 2, flying alone through the dark, continues to prove it, one data point at a time. If this video made you think, share it with someone who would appreciate it. Subscribe if you haven't already. We break down real space science in a way that actually makes sense. And leave a comment below telling me, what do you think we'll find when we finally send a dedicated probe to interstellar space? I'll see you in the next one.